So good evening all. Today we discuss about Hall effect. So when a magnetic field is applied perpendicular to current carrying conductor, a voltage is developed across the specimen in a direction perpendicular to both the current and magnetic field. This phenomena called as that Hall effect. The voltage so developed is called the Hall voltage. So in the consider a slope of material subject to an external electric field Ex. So along the x-axis and a magnetic field and h is along z axis. As a result of the electric field, current density Jx will flow in the direction of Ex. So let the current be carried by an electron of charge. The external magnetic field applied perpendicular to the current will be in exact transverse magnetic deflecting force on the electron, which causes the electron to drift downward to the lower edge of the specimen. So consequently, lower surface of the slab collects the negative charge and upper surface is of a positive charge. This excess of negative charge of the lower edge and the corresponding excess of a positive charge at the upper edge creates a transverse electric field EY, is known as the Hall electric field. So which opposes the transfer drifting of electrons ultimately, and equilibrium is reached in which the force due to the accumulations of electrons become equal to the magnetic force, and so the flow of electrons stops. So the net force of electron is becomes zero, so that is F of I equal to 0. So the electric force on the electron having the charge minus E equal to minus E EY, and we know that the current density is given by J equal to minus EV. So therefore Vx equal to minus Jx by Ne. So therefore RHS equal EY equal to RHS Jx Hz, and this is the Hall effect is described by the means of a Hall coefficient RH equal to minus 1 by Ne. So it's called the Hall coefficient for the substance of the bore. The negative value of the RH indicates the current carriers or electrons. If the charge carriers are the holes, RH is the positive. And the applications of Hall coefficient and mainly we discussed relation between RHS and mu. So mobility mu is defined as the velocity acquired by the current carrying particle per unit electric field, that is mu equal to Vx by Ex. So therefore RHS is equal to mu dot 1 by sigma. Therefore sigma is already, we know that the electrical conductivity of the metal. So therefore mu equal to RH sigma. And application of Hall effect. So the Hall effect measurements provide the following information about the solid. The sign of charge carriers are determined, that means electrons or holes. The carrier concentration and the number of charge carriers per unit volume is determined. The mobility of charge carriers is measured directly. So we can decide whether material is metal, semiconductor or insulator. From the knowledge of measured Hall voltage, unknown magnetic field can be measured, provide the value of a Hall constant for the slope is known. And the Hall coefficient of RH is negative of an N-type semiconductor and positive P-type semiconductor. Thus the sign of Hall coefficient can be used to determine whether even semiconductors are semiconductor is N-type or P-type. The calculation of carrier concentration RH is equal to minus 1 by Ne. So we know that Ne equal to P equal to 1 divided by RHS, number of electrons and determination of mobility I already discussed. The conduction is due to one type of carriers, the electrons sigma is equal to mu upon therefore mu is equal to sigma over h. So we know that the mobility of the charge carriers. So in the measurement of magnetic flux density, the Hall voltage is proportional to the magnetic flux density B. So for a given current, so the Hall effect can be used as the basis for the design of magnetic flux density in a metal. And thank you. So see you in the next series.